So in this segment, I'm going to talk about a way to be faster and more efficient with complex multiple choice questions. The problem that you have is that your memory capacity is limited. For most of us, the capacity is about 7 things. If you try to hold too many things at once, you feel confused, a feeling that's called cognitive overload. What you can do on multiple choice questions that are complex, which have a tendency to overload working memory, is you can keep track of the different pieces by writing notes or sketches on the exam. And you can practice the kinds of ideas and questions that you might need in advance. In the question below, there's too much to hold in my mind. Let me underline them and number them. We have transcription factors. They bind to DNA, signaling molecules. They bind to receptors. There are second messenger molecules. They bind to proteins. 1, 2, 3, 4, 5, 6 different things. They bind with high specificity, that's 7, and low affinity, that's 8. Which of the following forces should be involved in binding? As you're thinking about this question, you still have to think about the answers, each of these, in relation to these 8 pieces. What I'm recommending that you try is to decrease the number of things you have to hold in your mind by doing sketches. So if, as you read the question, you make sketches or put in keywords, you can start capturing ideas without having to hold as much in mind. As I read, transcription factors binding to DNA, and of course I have to know what those are. There's a transcription factor bound to DNA, a signaling molecule bound to a receptor, a second messenger molecule bound to some protein. They all bind with high specificity but low affinity. Each of those is about binding. It's actually the same thing in all. High specificity means they attach specifically only in that location. Low affinity means they bounce off quickly. Ionic bonding is plus and minus charges interacting with each other. Those are strong forces, but in water, they can be easily disrupted. So that's a possibility. Van der Waals forces are about molecules that are close to each other being attracted. So that's certainly a possibility, because when binding happens, these pairs of molecules are close to each other. Hydrogen bonding is happening with weak charge interactions, so that's a possibility. Covalent bonding is an actual shared electron, at least one, between 2 atoms. And covalent bonding is strong and hard to break, so that's unlikely. So at this point I have 2 possibilities, a third one that's a question mark, and then we're down to A, B, and C are all likely to be involved for different receptor ligands. I'm confident that B and C should be involved. I'm unsure about A, so I'll go with E. Let me do this again. I'm going to erase. You might want to time how long it takes to do it.
So I'll be showing you sketches that I would make if I was being very detailed. You can choose for yourself how much detail you want to add. I'm skipping things I remember. I didn't draw the DNA under transcription factor. Showing a binding pocket. I draw an arrow with only, reminding me that only the specific ligand will bind, and it has low affinity. So it's bouncing off easily. I'm thinking through the different pieces, sketching van der Waals, hydrogen bonding, which is weak plus minus charge interactions. Covalent bonding is strong, I cross it out. Okay, let me try it again for another question. Tight junctions, there's the basement membrane. The laminins are in the basement membrane according to the question. There's the gene, laminin gene, coding, regulatory region, mutation in the regulatory region. And I know that would give me more or less laminin, depending on whether it was a mutation in an enhancer or a repressor. Laminin has nothing to do with muscle contraction. I can't imagine how it is affected by heat or light. Cytoskeleton maybe, but that's inside cells, so there's a cell with cytoskeleton. tight junctions? Maybe. Those are holding cells together, so maybe, but last one, tougher, more rigid integument with more laminins, I'd have more tougher basement membrane. That one now makes sense. I'll go for E. Again, sketch only what you need. Here's a cell. We might expect it to deflate like a water balloon, all the contents leave. But often that doesn't happen. So cytoskeletons inside the cell. With a cut, some water might come out, but if the membrane is held in place, most of the water will stay, most of the contents will stay. Much of the water might be attracted to positive and negative charge. That would hold it in as well. The extracellular matrix around a cell is attached to it. And so if the cell boundary membrane is broken, we might still have that cell staying pretty intact, same shape, and so not much water escapes. With the sketch, they all seem reasonable. Here I would decide how much to put in, but if I'm going to be thorough, here's Tin Man. P increases Tin Man. Q decreases it. Oh, and I'm going to remind myself it's the number of cells. So with P allele, there's more cells that express, and with the Q allele, less cells. And later I'll remind myself that might make a bigger heart. So P might give a bigger heart because more cells are expressing Tin Man, which induces hearts. I write out P squared plus 2PQ plus Q squared because I think I might need it. Tells me P equals 0.7, P plus Q equals 1. So Q equals 0.3. Now it says large size. That makes sense to be P squared or PP, both P alleles. Intermediate would be PQ because they're codominant. And small size would be QQ. So big hearts for PP, small hearts for PQ, intermediate for PQ. 2PQ equals 0.7 times 0.3. I realize I forgot to write times 2, so times 2, it equals 0.42. 2PQ equals 0.42, hearts of intermediate size at a frequency of 0.42. Okay, it's under natural selection. Genotypes PQ. They're doing better. P squared, PP, and QQ are doing worse. So that's what selection is doing, favoring PQ. We're talking about heart size. And Q squared, P squared are small and large hearts. PQ is intermediate size. They do the best. The extremes disappear. And I might recognize that right away as stabilizing selection. Or I might decide I need more sketches. Disruptive selection, where it's against the middle. That would be against PQ. That doesn't fit. Directional selection, one extreme we get rid of. And so the mean shifts. That doesn't fit. Stabilizing selection, we get rid of the edges. The middle does the best. That fits. Immediate selection, never heard of it. Doesn't turn out to mean anything. Frequency-dependent selection, selection against the more common phenotypes.